Hello friends, I welcome you in lecture number 35 on relations. In this lecture also we are going to discuss one more question on determination of equivalence classes. This question was asked in GTU Summer 2020 exam. Question is define equivalence class. Let R be the relation on the set of integers. Here it is denoted by capital I, defined by R equal to set of all those ordered pairs xy such that x minus y is an even integer. Find the disjoint equivalence classes. This is another notation for the set of integers. Generally we are using this capital Z to denote the set of integers. And here given relation R is defined on the set of integers, that is R is a subset of Z cross Z, or it is a subset of I cross I, and R is given by they have taken all those ordered pairs xy such that x minus y is an even integer. X minus y is an even integer if it is multiple of 2. So here I can write x minus y equal to say 2n, where n belongs to z. So you can see x minus y is an even integer, that is x minus y equal to 2n, or we can say that x minus y is multiple of 2, or 2 divides x minus y. So this relation R is nothing but congruence modulo 2 relation. We have already seen this congruence modulo relation. In previous lecture we have considered congruence modulo 3. Here this relation is congruence modulo 2. X minus y is an even integer if x minus y is a multiple of 2, that is x minus y is divisible by 2, and therefore R is nothing but congruence modulo 2 relation. And we know that congruence modulo relation is always an equivalence relation on the set of integers. Therefore we can talk about equivalence classes, and here we have to decide disjoint equivalence classes. So we start with 0. First we find out equivalence class generated by 0, which is in this set of integers. So for 0 belongs to I, by the definition of equivalence class, 0 equal to, we have to consider relatives of 0, that is we have to decide all those integers y such that 0 is related to y, and by the definition of relation R, 0 is related to y if difference of 0 and y is a multiple of 2, or we can write 2n for some n in this set of integers. We are interested in the value of y, so y belongs to I. 0 minus y is minus y equal to 2n, n belongs to z, and this I can again rewrite as y belongs to I such that y equal to minus 2n, n belongs to z. And for different values of n we will have different values of y. If I take n equal to 0, I will obtain 0. For n equal to 1, I will have minus 2. For n equal to minus 1, I will have 2. For n equal to minus 2, I will have 4. For n equal to minus 3, I will have 6. So you can see the pattern here. First I have written 0. If I am adding 2, I will obtain second element. Then 2 plus 2, that is 4. 4 plus 2, that is 6. And you can see pattern on this side also. If I subtract 2 from 6, I obtain 4. Then 4 minus 2 is 2. 2 minus 2 is 0. 0 minus 2 is minus 2. And minus 2 minus 2 is minus 4. And this will continue. So this is the equivalence class generated by 0. and all the elements are nothing but multiple of 2. Equivalence class generated by 0 is nothing but set of all integers which are multiple of 2. Now we consider equivalence class generated by 1. For integer 1, for 1 belongs to I, equivalence class generated by 1, this is equal to, consider all those integers y such that 1 is related to y. And by the definition of relation R, 1 is related to y if 1 minus y is an even integer, that is 1 minus y equal to say 2n, n belongs to z, and we are interested in the value of y, so we can rewrite this equation as y equal to 1 minus 2n, n belongs to z. Now if I take n equal to 0, I will have y equal to 1. If I take n equal to minus 1, I will have 1 minus 2 into minus 1, that is 3. If I take n equal to minus 2, I will have 1 plus 4, that is 5. And this will continue on this side. If I take n equal to 1, then I will have 1 minus 2, that is minus 1. For n equal to 2, I will have 1 minus 4, that is minus 3. And for n equal to 3, I will have 1 minus 6, that is minus 5. And this will continue. Here also we can see the pattern. If I add 2 to minus 5, I will have minus 5 plus 2, that is minus 3. Minus 3 plus 2, that is minus 1. Minus 1 plus 2 is 1. 1 plus 2 is 3, and so on. So this is the equivalence class generated by 1. And now we check the equivalence class generated by 2. But you can see here 2 is in the equivalence class generated by 0. That means 0 is related to 2. And it is obvious that 0 is related to 2 because difference of 0 and 2 is an even integer. Therefore, equivalence class generated by 0 and 2 must be same. Using the property of equivalence class, we know that if two elements are related, then their equivalence classes are always equal. And we also know that all these elements in this equivalence class are nothing but those integers which are related to 0. Therefore, equivalence class is generated by 2, 4, 6, minus 2, minus 4, minus 6, all are equal to equivalence class generated by 0. Same thing here, all these elements are nothing but relatives of integer 1, so they are related to 1. Therefore, equivalence class is generated by 1, 3, 5, minus 1, minus 3, minus 5, all are equal to equivalence class generated by 1. Therefore, we have only two disjoint equivalence classes, equivalence class generated by 0 and equivalence class generated by 1. And we can observe that these two equivalence classes are disjoint because 0 is not related to 1. Difference of 0 and 1 is minus 1, which is not even integer. So 0 and 1 are not related, therefore their equivalence classes are disjoint. There is no common element in these two equivalence classes. Here we have odd integers, here we have even integers. And if we take their union, then we will obtain set of integers. Union of these two equivalence classes is nothing but the set of integers. So these two are required disjoint equivalence classes. Therefore, there are only two disjoint equivalence classes generated by 0 and 1. So this is the final answer to our question. Find the disjoint equivalence classes, and we obtained only 2 disjoint equivalence classes. Now I can remark, or I can note down certain things which we have observed from last 2 lectures. Suppose if you recall the previous lecture, in previous lecture we had taken this congruence modulo 3 relation, and we obtain 3 equivalence classes generated by 0, 1 and 2. These 3 equivalence classes were disjoint, and this collection was partition of the set of integers. So if I have congruence modulo 3, I have 3 disjoint equivalence classes, and in this lecture we have seen congruence modulo 2 relation, and we find that we have 2 disjoint equivalence classes and their union is the set of integers. So here this partition contains 2 disjoint equivalence classes. So this is in general true if I have congruence modulo m relation. Suppose I have congruence modulo m relation on the set of integers, then there will be exactly m disjoint equivalence classes, 0, 1, 2 and so on up to m minus 1. If m is integer, m is natural number greater than 1, and we have congruence modulo m relation on the set of integers, then this collection has m equivalence classes or m blocks, and this gives us the partition of this set of integers denoted by z or I. So remember this note or remark, and whenever they ask you to find out disjoint equivalence classes corresponding to this congruence relation, then you can remember this remark and you can verify whether you have obtained required number of disjoint classes or not. If I have congruence modulo m relation, then I must have m disjoint equivalence classes. Sometimes they ask you to find out the partition of a set of integers corresponding to given congruence modulo m. So in that case you can mention that here for example in this question, if they ask you to write down the partition of z corresponding to given relation, then you can write that this collection of 2 disjoint equivalence classes is a partition of I, because these two are subsets of I, their union is I, and they are mutually disjoint, that is their intersection is empty set. And remember this remark that if we have congruence modulo m relation on the set of integers I or z, then this collection is having m equivalence classes generated by 0, 1, 2 up to m minus 1, and this always gives us a partition of the set of integers denoted by z or I. So this is all about this session. I hope you like it. Thanks for watching.